All right, on to the very last electrical PowerPoint. This one's just talking about lighting types and fixtures. A lot of this will be recaps, so I'm not going to go through as much in depth on this one. But I'll talk a little bit about what light is, the different general types of lamps that we deal with, some different lighting types. Fixture types is, I mean, that's a huge animal in itself, and that's dealing a lot more with interior design type stuff at that point, where there's a lot of additional coordination efforts that have to take place. But I'm not going to go into that because you talk about that stuff forever with all the different fixture types. Um, and then measuring light, so different couple ways to measure light. So what is light? Light is a form of energy that can be released by an atom. So the reason why I like to talk about it is because I think it's not only a cool concept, but it's also important to understand, I think, just how it works in general. So technically what it is electromagnetic radiation that's visibly detected through various wavelengths. So we're seeing the different wavelengths within. It's also made up of small particles that have energy and momentum, but no mass. Those particles are called photons. So they are the most basic unit of light. So what we're trying to do is create that through electricity. There's an extremely wide range of wavelengths that make up the overall spectrum, from gamma rays to radio waves, but what we see is the visible light spectrum. So anything from our frequencies of 750 down to 380 with our terahertz, and then our wavelengths of 400 down to or up to 780. So this is our visible light spectrum that we're dealing with. Moving into lamps and bulbs. So there are three basic categories of lamps. We have incandescents, we have fluorescents, and LEDs. Just kind of break down how those all work, and there's a couple different subsettings of those as well. So your incandescents are your most basic. The lamp lights by electrical current passing through a filament. We generally use tungsten as that filament, and that tungsten is within a vacuum bulb. So that bulb often contains some sort of inert gases like argon or nitrogen instead of just being a pure vacuum. If we used oxygen, that would disintegrate the filament, and that was one of the issues that Edison was running into for a long time, was having oxygen introduced. So parts of the incandescent bulb just kind of shown here. We have the contact wire that comes into the base. We have the supporting wires for our filament, which is the tungsten. We have our contact wires that come down to the foot, which is down here. There's electric contact foot. As we turn that circuit on, the power comes up. It doesn't ignite, but the heat that is generated makes that filament glow within the bulb. Some of the big advantages of this are they're very cheap, they're inexpensive to make, they're the most common form. They give off what people consider soft and comfortable light, although we can adjust that a little bit. A lot of different options for how we use them. They turn on instantly because that power immediately is coming through and makes that filament glow. And they're also dimmable, because if we have a dimmable light where we're not giving them as much power, there's not going to be as much glow coming through. Some of the disadvantages then, they are relatively inefficient, so they do have higher operating costs in general. Up to 90% of the energy it uses is for producing heat to light the filament. So instead of just providing light, what we're doing is you're using heat to produce that light, so that's where a lot of that energy is consumed. It's also got a relatively short life cycle, because as that filament is heating, it's constantly slowly wearing away. They are also, like I mentioned, they're dimmable, but sometimes that dim bulb buzzes due to that filament vibration. So if we're giving it a little bit less current coming through, it's not vibrating as fast with the wavelengths. So you're hearing that buzzing sound. Halogen is a form, I'm sure we've heard of them before, but they're a form of incandescent lamps. The big difference is, we're still using the tungsten filament. We're using a much smaller envelope, and that envelope is made of quartz instead of glass due to the close proximity of heat from the filament to the envelope. And that bulb is then consisting of halogen gas, or a gas in the halogen group of gases. You don't need to get into that level of depth though. So xenon bulbs are also halogen bulbs, but use xenon as the inert gas. So they're all different forms of incandescence. So they look something like this. Obviously, we see these a lot. They produce a lot of power, or a lot of light. The advantages, roughly the same as the incandescent bulb, but they are a lot more energy efficient than your traditional incandescents with tungsten. The halogens, that gas works with the tungsten to keep the filament intact a lot longer. The inner coating reflects heat back to the filament, so we're technically recycling that heat within. and they do have a lot lower operating costs. Disadvantages, they are definitely more expensive upfront than your traditional incandescents. So that's the big disadvantage there. Fluorescents are a different animal in their own. They are a lot more complicated in the way they operate, but they're still very common. So the way they work is we have light that's emitted through photons by ionizing mercury vapor within a glass tube that is coated with phosphor. It's quite a bit more complicated, like I mentioned. We're not just heating a filament to produce light. So we want to understand a little bit how that light is produced, so we understand how the photons work, going back to that. So electrons within an atom have different energy levels. Um, it includes the speed and the distance from the nucleus that they are. That distance from the nucleus indicates how much energy it has. So the electrons that are further away from the nucleus have more energy than the electrons that are closer to the nucleus. So in order for an atom to release those light photons, what has to happen is that electron must release energy. So the way we have to do that is we excite them. Okay, we excite them by adding some heat to boost the electron to a higher orbit. And we only do that for an instant. So while it's at that higher orbit, it gains more energy, but then it loses that energy and falls back to its original orbit. The way when it falls out of orbit, it releases the energy it had, and that energy is released in the form of a light photon. The wavelength of light depends on amount of energy that's released. So the different types of atoms that release different light photons. So that color is determined by the atom, that type of atom. Because again, going back to that wavelength and the visible light spectrum. So all light sources work this way, but fluorescent lamps have a more complex system than others. So it's the components and the pieces of it, because again, we're not just heating a piece of filament. So we have contact pins, we have the tube or the glass, we have an inert gas that's usually argon that's inside. There's normally a small bit of mercury as well. That's why we don't want to be breaking them all over the place and as we're throwing them away. We also have a phosphor powder coated internal coating. The electrode there's an electrode at both ends, and we are wired to the electrical circuit at both ends. So the current flows through an electrode, causes that electron to move from one end to the other. Energy changes some mercury from liquid to gas, and the electrons collide with the mercury atoms, which excites the electrons. That mercury electrons then give off the UV light, which is not visible to humans. So when those electrons are giving off light, we need to actually be able to see them. So that's where we have the phosphorus gives off the visible light when exposed to the UV light. So the electrons getting excited about the UV light. Oh, but sorry, I just kind of backtracked there a little bit. So as the electrons are getting excited by the UV light, they're giving off the light for the phosphorus that it can actually reflect in. Another dad joke. Fluorescents are very exciting. So this is how they look. This is how they work. The advantages are definitely a lot more energy efficient than incandescents. There is better and more consistent light distribution. They have a longer lifespan because our contacts don't wear out as much. We have a wide range of options. And then the disadvantages, though, are they are more expensive than incandescents to start. The concern with health and environmental hazards because of chemical leakage. We have frequent switching on and off can cause quick degradation of this filament at the very end on the contact pins and the electrode. And older bulbs tend to buzz due to the ballast not regulating voltage properly. So the ballast is what's controlling how much energy is coming in. Different types of fluorescent bulbs, I'll let you guys go through that as well. Just understanding T8s, T5s are most commonly used. T5s are smaller, more energy efficient. T indicates the shape, so tubular. Okay. And then the number indicates the size in eighths of inches. So 5 is a 5/8 inch diameter, 8 is an 8 inch or 1 inch diameter bulb. CFLs are compact fluorescents, same general concept as your fluorescents, but have an integral ballast. We'll talk about ballast in a second. So these require a little more energy when they first turn on, but once electricity is starting to flow, it runs much more efficiently. The process is much slower though, which is why it takes a few minutes for CFLs to get to optimal light. So if you've ever used CFLs, you'll notice when you turn them on, they seem very dim. It takes them a little while to get going. Once they do, they're pretty bright. So here's your parts of the CFL. The big difference again is we have our integral ballast within the bulb itself. Some advantages. much more efficient than your standard fluorescent even, and incandescent, about 70% less energy used than an incandescent. The small size and unique shape fits them with standard light sockets, which is a big benefit of theirs. Some of the disadvantages are your same with fluorescents, but also they are slow to start. Sometimes they take up to even 3 minutes to get fully intensified. All right, I mentioned ballast a couple times. Your ballast is a component that regulates the amount of electrical current that comes into a lamp. Your fluorescents and CFLs need that ballast. Too much current would blow out the lamp without having, without having your ballast in place. A couple different types: magnetic, which is shown here, and electric or electronic, which is shown here. These are a lot more common nowadays, just more modern form of technology. LEDs, the last type of bulb that we'll talk about. Your light emitting diode, if you know what that stood for. The diode is basically a solid state technology, so SSL, you'll see that term. It's called solid state lighting. That means that we're emitting light from a piece of solid matter. So not all diodes emit electromagnetic energy as light. Some only emit heat. But what we're talking about is the lighting type. And we've actually been using LEDs a lot for like indication lighting, but not really for space lighting until a lot more recently. Now they're becoming so popular that the cost is coming back down and really significantly increasing the advantage to use them. Two different types. We mentioned indicator, right? So things like this we've been using for a long time. And then illuminator, which are a lot more high powered. This is what we use as one example of how we would use LEDs. So your LEDs generate light through two different semiconductors that are located between electrodes. So the semiconductors, we have N-type, which are negatively charged, and P-type, which are positively charged. Your N-type has extra electrons, and your P-type are lacking electrons, so there are holes for electrons to fit in. So as the current flows across the semiconductor junction between the two sides, from negative to positive, they emit light. So you see here we have N-type, which has extra electrons, and P-type, which has lacking electrons. They're going to be flowing back and forth across this junction. And as they flow across that junction within the solid state matter, then they are emitting light. So instead of using a ballast, they use a driver. That driver is what regulates power to the LED. The drivers actually have the ability to regulate power to a single LED light, depending on how the fixture is set up, or to a string of LEDs. They provide that constant uniform current. They're a lot more efficient than a ballast. They use the big issue here, though, is we use DC power instead of AC power, so they do need to have a converter in there. So again, just another explanation of how an LED actually works. I'll let you guys go through that as well. So the big advantages, definitely the most efficient type that we would use. Approximately 80 to 90% of the energy supplied is converted to light, and only about 10 to 20% is lost to heat, which is a big deal. If you remember from incandescence, it was pretty much the opposite of that. They have a long lifespan, about 60,000 hours. That should be about 20 years if operating 8 hours per day. The temperature and impact resistant, so they're made of aluminum, gallium, and arsenide, or similar types of materials. And they're generally a lot more environmentally friendly, although I did mention that if you see the last slide here, they're dealing with silicon, and there's obviously some issues with silicon mining and how that has to take place. But in general, with the actual product, once we have it, it's a lot less toxic and 100% recyclable. Different advantages or disadvantages, they do have a higher initial price, but because they're becoming so common, right? The supply and demand is changing. The supply is getting a lot higher. The technology is getting a lot better. So the price is definitely coming down and being right in line almost with incandescence and fluorescence in a lot of situations. They are temperature sensitive though, even though it is one of their advantages. They're generally resistant of it, but they do have some issues where, say for instance, we have very high temps or very rapidly increasing temps like mils could be a problem. So that's why we stick with more halogens and things like that. I'm not going to go through this too much, but different types of lighting. We have, the terms ambient lighting is that even distribution within your facility. That's your primary lighting. Accent lighting is creating focal points for different specific things within your facility. a lot of times architectural features. And then task lighting is for something that's very specific task. So right over top of like a sink or a cooking surface, right? Desk work, things like that. So ambient light is your main source of light. Accent is promoting some sort of focal point, and task lighting is for that specific task. The other ones, all right, so if we're looking through here, we have accent on the side, we have task looking right over top of the cooking or sink, can't quite tell what that is, and ambient is your main lighting. The other one is day lighting that we use, obviously, if we have any windows, which we obviously need to have, but using skylights, using solar tubes, stuff like that to provide additional natural light within the space. All of it gets calculated into how much that individual room needs. So daylighting and daylight harvesting. Daylighting, like I said, just natural light, windows, skylights. The more natural light allowed in, the less overall energy efficient the room and building becomes, though, right? Because what we have a problem with is the more glazing, there's less insulation, and then even though we have the insulated glass, they're not as insulated, they're not as protective as the wall assemblies. So even though we have less electrical costs for gas, you might have more less electrical costs for lighting, we might have more electrical or gas costs for the mechanical equipment to make up the air differential. So again, we have trade-off issues. So there are what the engineers are constantly looking for is what that optimum trade-off is, where we get the most benefit out of daylight without having to use so much energy with our lighting, without having to sacrifice too much in extra mechanical work for maintaining the balance of the comfort in the space. One of the cool new pieces of technology that I'm a big fan of are called solar tubes, because we've always run into problems historically with skylights, especially up in these northern climates where they tend to leak a lot. The solar tubes use much less square footage than skylights. They disperse natural light throughout space, and they're a lot less prone to leaking. They're a lot less prone to having condensation build up around them than traditional skylights. And the other cool part is you can actually take them from your roof and run them through walls or through chase walls or whatever in your houses or your whatever buildings and run them into basements. So as long as they need to go, so you can get natural light into any floor of your house. The term daylight harvesting is important for energy efficiency as well. It's a combination of understanding how many foot candles we need or whatever is required for different spaces at different times of the day. And we use natural light to offset the amount of electrical lighting needed. So we use a lot of sensors for this. It indicates how much ambient lighting is needed in that space. And as the sun's coming up or as the clouds are going away and the lighting is getting brighter naturally, then those sensors talk to your light fixtures themselves, and those light fixtures dim so they don't have to use as much power. So just look like any other sensor you would see. Here's the fixtures types. As you can see, we go through here. You can go through all this stuff on your own to see what all these different terms mean. There's a lot of different fixture types. Obviously, there's, I don't know, probably infinite amount, but just a bunch of different slides talking about those things. The big thing to understand, though, is the coordination challenge with all of it. There are lead times that we have to deal with. There's a lot of different trades involved with installing those fixtures. Understanding the weight of fixture plays a big role with how much backing is required, where that's going, what subs we have to get involved. Cost also plays a huge factor when it comes to light fixture types. So a lot of times in your electrical package, if you're getting a little bit too expensive, you're wondering why, take a look at your fixtures, see if there's other ways we can maybe go after it. Sometimes the lead issues are a big deal as well. Okay, the last thing we'll talk about here is measuring light. So we have to measure light in two ways, brightness and power consumption. Brightness has two ways of measuring it. We have lumens and we have foot candles. So lumens indicates the light output or the brightness of a bulb. So it's used for identifying the light bulb brightness. Foot candles is indicating how much light is on a surface that is being lit. So it's used for identifying how well lit a space or surface is. Again, I tend to get to this point of the semester, I like to add dad jokes in there, but so the foot candle is trying to figure out per code what our lighting is within the space. The lumens is how bright the actual bulb is, and there's a combination of all of that for different spaces to figure out how do we meet those code requirements. So look, a foot candle is technically actually the brightness it would be if you put one candle on the floor at your ground or foot level. So that's about what a 1 foot candle would be. Power consumption then is calculated in watts, so it's the amount of energy that's needed to use the bulb. So for energy efficient purposes, what we are trying to do is to use the least amount of wattage for the most amount of lumens. And that lumens then indicate or sort of translates into what my foot candles are in for different space. So just a chart showing the combination between incandescents and LEDs, what our minimum light output would be, what the wattage would be for the lumens. So you can see here, 15 watt incandescent would be 2 to 3 watt for LEDs, giving us 0 to 200 lumens. So your general incandescent bulbs, a lot of them are in the 60 range. So instead of 60 watts pulling in, your LEDs would be 7 to 9, getting you somewhere in that 500 to 700 light output for lumens. The other thing we have to figure out is light color or temperature. So Kelvin is the scale that we use to indicate the temperature associated with light color. We're talking temperature with color or with lighting. It's not heat, it's color. So we look at a Kelvin scale. So a 2700 Kelvin is your warm white, so your traditional like incandescent bulbs, up to about 6500 K. I've seen 7000 K too. These are like more daylight, so it's what we would call like a blue light almost. I think a lot of people sort of find this 3000 to 3500 a little bit more of that comfort spot where it's not so 1970s looking over here, but not so blinding clean room over here. So generally speaking, I like to keep my rooms around 3000 to 3500. A lot of your new LEDs can control how much K you want in within your system or within your space. So that's all I have on lighting types, and we have one more for low voltage and controls, and then you will be into your assignments in your group project.